In this video, we're going to look at the equations and some problems associated with motion in one direction. So let's look at the first equation. First equation has to do with the acceleration definition. I don't have it fully down here, but this is enough. It's the rate of change of velocity. So just going by what we're saying there, the rate of change of velocity, we can get the first equation that we need. So the change in velocity. So just like finding the change in anything else, we need to do something. We need to subtract. We need to subtract the final velocity from the initial velocity. That's going to get us our change in velocity, which sometimes be written like this, delta V. The delta stands for the change in, and it's going to pop up in other places in this class, right? If you look at other books or websites, you're going to see that symbol change of, right? So the change in velocity, final minus initial. So that's the velocity at the end minus the velocity at the initial. That's going to give me the change. But it's more than that. It's the rate of change. So not only do we care about how much does the velocity change, but we care about how fast did that change occur. So if we want to factor into the time it took for that change to occur, divide by time. So there is our first equation. Change in velocity equals time, and that, or change in velocity over time, and that equals initial velocity. Okay, so that one comes right from the definition. The second equation just comes from experimentation, and we will at some point conduct the experiment for this one. But what's it telling us? It's telling us the displacement equals the initial velocity times the time plus 1/2 acceleration times time squared. So this one's a little more of a complicated equation. Now, these are the two that we need to know. If you look other places, you might see other equations, but these are the two equations that govern this chapter. Every other equation you see is some rewrite of one of these two or some combination of these two. For example, right, it's certainly common to rewrite this equation and solve for final velocity. So if I want to get final velocity by itself, I'm going to multiply both sides by time, acceleration times time, and then I'm going to add the initial velocity to it. And now I have this, right? Is it a new equation? No. It's the same equation written in a different way, right? So we'll see a lot of these equations pop up. Other things that are very common is someone will take this equation and they'll take all of this and they'll substitute it for acceleration. So we could write that displacement equals initial velocity times time plus 1/2, and then it's final velocity minus initial velocity over time times time squared. This is going to cancel out one of them, and now I have a different equation. Is it really a different equation? No, it's these two equations combined. So we could see all kinds of combinations of these equations. What I recommend you do is you memorize these two. Memorize this equation, memorize this equation. To be honest with you, if you're doing the work in class and you're doing the homework, you're not going to need to memorize them. You're going to know them anyways because you're going to use them so much. But either way, I encourage you to know these two equations and then learn how to do the algebra to solve for other things. All right, so there's the equations we're going to be using. The other thing that becomes important is how do we tackle problems. One of the things that I hope you start to figure out if you're not, if this isn't a strength of yours, is how to set up problems and how to solve them. There's going to be a decent number of problems that when you look at the question, you're not going to know how to come at the answer. You're not going to be able to just say, okay, this is what I got to do to get the answer. It's going to be more complicated than that, right? So one of the things that we try and stress in class is to come up with a system, right? And come up with a system that's going to allow you to solve the problem, even if when you start it, you don't see where the end point's going to be. And if you come to me with questions, I'm going to expect you to go through this. When I look at your work, I'm going to expect you to go through this, right? So it doesn't really matter if you're good at this or not. I'm expecting you to be able to do these things. If not at the beginning of class, certainly as we get into the class more and more and more. And the steps are pretty simple. First thing we do is we draw a diagram. Drawing a diagram becomes very important, partly because we're dealing with vectors, right? And therefore we need a diagram so we could establish direction, right? So that's one of the main things. And also, if we could draw a diagram, we can visualize what's going on in the problem. And it's amazing how many times people say they don't understand a problem, and then when I ask them to draw a diagram, they simply haven't spent the time to figure out what's going on in that problem. If you don't understand what's going on in the problem, well, then you can't solve it. Next step is you list your known values, right? It's a nice thing about math classes and physics classes and a lot of other types of classes. If you read a problem, the numbers are in the problem and there's no extra numbers and they don't leave out numbers so you couldn't possibly solve it. They don't say in the problem, all right, go find these numbers, come back and solve the problem. They say these are the numbers, use these numbers, right? So they just give you the numbers you need, which is not like life, right? If you have to do something, you're an engineer, you're a scientist, you got to figure out what numbers you need to go get, and then you got to figure out how you're going to use them, right? It's a little more of a complex problem. So in the problem, we need to list our known values. Next thing we do is we list the possible equations. Again, the nice thing is that we only have 2 equations right now. As we get more and more into this, we're going to see a lot more equations. And then we adjust the equations as needed. And then we solve, and we solve using unit analysis. So I have a video on unit analysis. We do need to get good at that. I'm not going to get into it too much now, but I will, when I solve these examples, use unit analysis. I will say I use it all the time. It doesn't slow me down at all. And in my video for unit analysis, I get into that. So I'll just leave it at that. But every time you do a problem that you're turning into me, I'm expecting to see that. All right, problem number 1. Car accelerates from 12 meters per second to 25 meters per second in 6 seconds. How far did the car travel in that time? All right, so I'm no artist, but I can certainly draw a road. Draw my car. I'll make my car red. Here it is. And it started at 12 meters per second. It moved along. Later on in time, 6 seconds later, it's over here. And it's now going 25 meters per second. So there's my diagram. And I am looking for this right here. Now, by making the diagram, I'm ensuring that I understand what's going on in this situation. And I'm establishing direction. Now, by drawing this, I've established that this way is positive. Now, why am I doing that? Because this is a positive 12 and the car is going to the right. This is a positive 25 and the car's still going to the right. So to the right's positive, right? I've made this statement. I don't know exactly which direction the car is going, but I need to establish some frame of direction so I can do this problem. I also know I'm looking for how far. Now, when it says how far, I don't really know if that's a length. I don't really know if that's a distance or a displacement. But in the end, when I look at this, this car's going in a straight line. So I can call it displacement. I could also call it distance because in this case, they're both the same. All right, so I need to start listing what I know. So let me back up 1 second. This is probably going to go over it, but let's see. If I look at these, I have 2 equations. I'll just go back to this and I'll write them up. I have 2 equations to use here, right? I have my acceleration equation. I have my displacement equation. And I know it's not the next step to list the equations, but I just want to make a point on this. Here are the only equations I have. So I know I'm using these right now because as we get into later chapters, I'll have more equations. But right now, this is what I have. But my point being, if I look at these 2 equations, I have acceleration, final velocity, initial velocity, time. Well, it's acceleration, time. These I already said. This one I already said. This one I already said. And then I have displacement. So there is 1, 2, 3, 4. Oh, there goes 4, 5. There's 5 measurements I could possibly know. That's a good thing to keep track of, right? When I'm looking at these problems, there's 5 things I could possibly have that would be useful to me. Right? Acceleration, initial velocity, final velocity, time, displacement. So which of these do I know? Well, I know my initial velocity, 12 meters per second. That's what I started at. I know my final velocity, 25 meters per second. I know my time, 6 seconds. So these are the things I know This and this are the things I don't know. So I've drawn my diagram. I've listed what I know. Now I need to figure out what equation I'm going to use. Well, I'm looking for how far. So I know that I'm going to be using this equation. I know that because this is the only equation that will give me a distance, right? It's a displacement equation. So it's the only one that I could use. When I look at this, what do I know? Well, this is known. This is known. Time again is known. I'm missing my acceleration and I'm missing my displacement. So I can't solve the problem with this equation yet because I'm missing too many things. If I have an equation and there's two unknowns in it, I can't do it, right? So I need to find acceleration first. So let's go to my acceleration equation. It's a little sloppy up here, but what do I know? I know my final velocity. Hold on. I know my final velocity. I know my initial velocity. I know my time. So I could use this equation to get acceleration. Then I can plug it in here and I can get displacement. So I'm going to clear some of this so that I can do my work. But what do I have? I have acceleration equals final velocity, 25 meters per second, minus initial velocity, 12 meters per second, divided by 6 seconds. Well, subtraction I can do. I don't even need unit analysis for it. I just need to ensure I have the same units. So I'm going to have 13 meters per second. That's a 13 meters per second divided by 6 seconds. And that works out to be 2.17 meters per second squared. Now, there's a couple things. It's a positive number. Acceleration's a vector. It could be positive, could be negative, but in this case, it's a positive number, which means it's accelerating to the right. And also the units work out to be meters per second squared, which we've already said are the units for acceleration. I'm going to say this a different way, though. Just this time, I'm going to say it this way, and hopefully it kind of helps. I can write this also as 2.7 meters per second Acceleration is the rate of change in velocity. So how much is the velocity going to change? It's going to change by 2.17 meters per second every single second. So I am not answering this question yet. I'm just talking about this. So my initial velocity was 12 meters per second. 1 second later, it changes by 2.7. So what is it? It is 14.17 meters per second. The next second, it's going faster. It's still accelerating. It changes by 2.17 again. And what is it next time? Next time it is 16.33 meters per second. And then the next time it changes by that again. Works out to be 18.5 meters per second. And it's going to keep speeding up and it's going to change by that rate every single second. So I have my acceleration. I know what my acceleration means. Now I can answer the question, though, how far did it travel? So how far did it travel? I use my displacement equation. Displacement equals initial velocity, 12 meters per second, times time, 6 seconds, plus 1/2, 2.17 meters per second squared, times 6 seconds, times 6 seconds. So, again, looking at unit analysis, seconds cancel out over here. I have 12 times 6, 72, I believe. 72 meters. And then I have, let's say I have 1, 2 seconds on the top, cancel out the 2 on the bottom. So I'm again, let's put this, let me do the math and then we'll put the units in. It works out to be positive, and it works out to be a positive 39 meters. So this is good because I'm looking for how far. I'm expecting my answer in meters, and all the units that are left are meters. And also when I do this addition, I'm adding two things that are meters. I get so there is my final answer, 111 meters. couple things tell me that I'm right. One is the units. Well, that's the biggest thing, right? The other thing is that the acceleration was positive, which makes sense. I'm moving to the right. I'm accelerating to the right. And then my final answer is positive, which means that the car is 111 meters in front of where it started. So a lot of things kind of give me some hints that I did a good job. And this problem is done. Let's look at problem number 2. Spaceship is traveling at 30 meters per second through outer space. Apparently that's not the way you spell outer space, but that's okay. When the engines are put in reverse, an acceleration of 6 meters per second squared is produced in the opposite direction. What is the velocity and displacement after 6 seconds? So here we go. Here is my spaceship. Let's see. Oh, spaceship's getting bad already. All right, so there's my spaceship. Traveling in outer space. And it's going 30 meters per second, and it's traveling this way. It has an acceleration of 6 meters per second squared, and that is that way. And I want to know a couple things. I want to know the velocity and the displacement after 6 seconds. So again, there's 5 things I can know: acceleration, initial velocity, final velocity, time, displacement. And which of these do I know? I know my initial velocity. It's 30 meters per second to the right in my picture. I know the acceleration. It's 6 meters per second squared, but it's in the opposite direction. So if to the right is positive, then to the left must be negative. This is partly where the diagram helps me understand what's going on, right? If I've established this direction to be positive, and I did by making this a positive number, well, this is in the opposite direction, so this has got to be negative, right? And we've got to know when to put those in. What else do I know? I know my time, and my time is 6 seconds. Now, let's look at the equations. Again, I could have 2 equations, so I'm going to write them both down. Well, I'm looking for a final velocity because the question is, what is the velocity after 6 seconds? So I'm looking for a final velocity. And this equation has final velocity in it. And I know this, I know this, I know this. Good. So I can use this equation to find final velocity. The other thing I'm looking for is the displacement. I could use my displacement equation. Let's take a look at this. What do I know? I know this, I know this, I know this, I know this. I know everything to find displacement, and I can find that, and I don't even need to readjust the equation. So that works out very nicely for me. I've got 2 equations. I got 2 things I'm looking for. I can use them to solve this problem. So let's go ahead and solve this problem. First one I'll do is final velocity. So there's my equation. Actually, here's my equation. I'm not going to rewrite it again, but I am going to rewrite it solving for final velocity. I'm going to multiply both sides by time, add initial velocity to both sides, and that's going to get final velocity by itself. Now I could plug in my values. Now I got to remember it's a -6, so it's -6 meters per second squared because it's in the opposite direction. And I know my time, 6 seconds, and then it's going to be plus 30 meters per second. Now, when I get my final answer, I'm looking for it to be in meters per second. And what else? Let's see. I'm looking for both of these to be in meters per second so I can combine them. Okay, -6 times 6 works out to be 36. It's negative 36. This cancels out one of these, so it's negative 36 meters per second plus 30 meters per second works out to be -6 meters per second squared. So I get a final velocity of -6 meters per second. Now the units work out to be right. The number certainly makes sense, and it's a negative value. So what does that mean? Well, if the spaceship was going to the right and it was accelerating to the left, that means the velocity was changing in the negative direction, or there is a negative change in velocity, which means the velocity is going to go down. It's going to go down by 6 meters per second every second. It started at 30, it's going to go down by 6, so it's going to be 24. It's going to go down by 6 again, so it's going to be 18. It's going to go down by 6 again, it's going to be 12, then it's going to be 6, then it's going to be 0, then it's going to be negative 6. It's changing by negative 6 meters per second every single second. That's what acceleration is, right? That's one way to define acceleration. And my answer is negative 6 meters per second, which means my final velocity, yeah, I could put it on my chart, but it means after 6 seconds, this spaceship is now going this way at 6 meters per second at the end of the 6 seconds. That's what it's telling us. It's telling us this is the direction it's now going, because velocity has a direction. So I know how fast it's going, I know what it's measured in, and I know the direction. All right, now displacement. Displacement equals velocity initial times time plus 1/2 acceleration times time squared. I had it already written, but I'll put it in again, and then let's just start plugging things in. 30 meters per second times 6 seconds plus 1/2 negative 6 meters per second squared times 6 seconds times 6 seconds. Now, I don't know if it's going to be positive or negative, but I do know everything has to end up in meters. So I have seconds up top, canceling out the one below. I have 1 here, cancels this one, this cancels this way. Or I guess I have 2 on top, 2 on the bottom. They still cancel each other out. And now what do I have? I have 30 times 6. Calculator's not on. 30 times 6, 180 meters. And then on this, I am going to have 1/2 times negative 6 times 6 times 6. Works out to be a negative number, negative 108 meters. I'm going to get a positive number, but it is in meters, and that's good. I'm looking for displacement. Displacement's in meters. Positive 72 meters. So where is it? Well, now this second picture is not really that good. Where is it? Well, it's still in front. So what do we have? I am going to... So let's just focus on our numbers for a second. We had an initial velocity. Oh, there. We had an acceleration. Negative 6 meters per second squared. We had an initial velocity of a positive 30 meters per second, moving to the right in my picture. We have a final velocity of negative 6 meters per second, which means it's moving to the left in my picture. The time that I cared about was 6 seconds, and the displacement that it turned out to be was 72 meters. So let's just focus on that and see what's going on. So I have this spaceship, and we're going to be looking at the spaceship like from above. So I'm just going to make it a circle. There we go. And this spaceship is traveling along, right? So this is the initial position. And what is it doing? It's moving to the right because I've established right is positive. So in my mind, it's moving to the right. But as it moves to the right, it is slowing down. So here it's slowing. And I know after 6 seconds it's going backwards, so it must be slowing. It must reach a point where it stops, and then it must start coming back. And then when it starts coming back, well, there it starts speeding up, and we'll see this more and more. But it starts at 0 in this second. After this point here, it's going 0 meters per second, and then it starts moving to the left, and it's starting to pick up speed. So after the 6th second, it's going negative 6 meters per second. So this is where it is now. With that in mind, I get a positive 72 meters. So what does that mean? Well, that means that the distance from my starting point, which is here, to where the spaceship is after 6 seconds, here, this distance is 72 meters. It's a displacement, so it's the straight line length between point A and point B. And that's 72 meters. Now, just to make one more clarification, right? Nothing shows it actually turning around in this picture. What's it doing? It's actually going this way, slowing down, slowing down, slowing down, stopping, and then it starts going backwards and speeding up, right? So it starts here, it ends here, and this distance is 72. So that all makes sense to me. I could see that it's going backwards. I could see it's 72. It traveled more than 72 meters to get here, right? Its distance is more, but this gets me its displacement. Where is it with respect to the starting point? It is 72 meters in front of its starting position still. Now, the second part of that was, what about after 11 seconds? So let's take a look at 11 seconds. It's not going to change too much for my math. Velocity final equals acceleration times time plus initial velocity, right? So I'm using the same equations. Displacement equals initial velocity times time plus 1/2 acceleration times time squared. It's already listed my known values. I already know my equations. I already have my diagram. I don't want to go back to the other slides. There's just not enough room on these slides. But I can still plug this stuff in. So what's final velocity? Final velocity is going to be -6 meters per second squared times 11 seconds plus 30 meters per second. Well, this is going to work out to be 66 meters per second, -66 meters per second, plus 30 seconds, -36 meters per second. And this one's going to be what? Well, we'll use another color just to make sure we don't confuse it. 30 meters per second. This time it's 11 seconds plus 1/2 -6 meters per second squared times 11 seconds times 11 seconds. Now, writing this out, again, to harp on you, I say I won't talk about it, but then I keep talking about it. Writing it out this way helps me organize the unit so I know what's going on. So looking at that, let's see, a second cancels out a second. I'm going to be in meters, which is good. And then I have 2 seconds on top, cancel out 2 seconds on the bottom. I'm going to be in meters again, which is also good. It also helps me not make mistakes. This is time, so I just write it once. This is time squared. I write it twice, right? A lot of people take shortcuts, but I don't make mistakes because I write everything out. And as you can see, it doesn't take that long. All right, so 30 times 11. 330 meters, and then it is 1/2 times 6 times 11 times 11. It's a -6, so it's a negative 363 meters. So works out to be a negative 33 meters. So there's my answers after 11 seconds. Now, what does that mean? Well, here was the spaceship to start. It was going this way. It slowed down. It stopped. It started going this way. It started speeding up. And where is it after 11 seconds? Well, it's still going backwards. So I know it's going this way. And I also know that the displacement is negative 33 meters, which means what? Which means now I know it's going backwards or to the left in my picture, and I also know that the displacement, the straight line length between A, the starting point, and B, the ending point, is 33 meters, but in the negative direction. So where is this spaceship? This spaceship is 33 meters behind the starting point. Again, it doesn't give me this distance of this blue line. It just tells me where it is with respect to the starting point. Up here, I didn't put a negative because my picture is saying, hey, it's that way, right? And that means negative in this picture. Looking at this a little more, though we won't do it in this video, one of the things that we could also calculate is we could also calculate the distance, but we can't do it in one step, right? This is nice displacement. I can plug it in, I can get it in one step. This is going to take more work. Okay, so that is 2, maybe you want to call it 3 problems. We're looking at how we calculate the numbers. We're looking at the unit analysis, so we understand if our answers are correct or not. And then just as importantly, we're looking to see what those numbers mean, right? And how they fit into the frame of the situation.